Okay, so in this video, we will consider limits at infinity involving roots, square roots, cube roots, and so on. And we have to be careful sometimes when we let x approach negative infinity and we have an even root. So let's see what I mean by this. Let's just consider first a square root. So look at the function y equals x squared. And we know the square root is the inverse function. And to find the graph of the inverse, we simply draw the line y equals x. And we reflect the curve y equals x squared about y equals x. And we'll get the graph of the inverse, which is the square root function. But as you can see, if you make the reflection, the curve that is what we hope the inverse is not a function. For any given positive value of x, there are two different y values. So we have to make a choice. And the choice we make, at least in this course, for numerical reasons, is we take the so-called positive branch of the square root. So we take the portion of the curve that is positive above the x-axis. And so we take this to be our function, y equals root of x, and we dismiss the negative branch. So for us, every time we take the root of a positive number, we get a positive number. Algebraically, we know there are two solutions. If you were to write root of 4, you could say it is positive 2 or negative 2. As 2 squared is 4, and negative 2 squared is also 4. But we reject negative values, and so we only keep positive values. So it's a choice we make. We choose to take the positive branch of the square root and not the negative branch. So always keep this in mind. A root of something for us positive is also positive, or in the case of x equals 0, equal to 0. But it's always non-negative. So you have to be careful. If x, we'll take two examples. What if you take, say, 3 squared? So you take 3, you square it, you get 9. And the root of 3 squared is the root of 9, which is 3. So you see, if you square 3 and take the square root back, you get back the number 3. What if you take negative 3? Now let's square negative 3. We get positive 9. And so the root of negative 3 squared is not negative 3, as negative 3 squared is 9, and so this is the root of 9, which is positive 3. And so you see, when you take the square root of the square of a number, you lose the negative sign. If you square something, you kill off the negative sign, and because we take the positive branch of the square root, the root of negative 3 squared is not negative 3, but positive 3. So you see that when you take the square root of the expression squared, you get back the same answer, but you've lost the negative sign. And so if you take the root of x squared, this is numerically the absolute value of x. Think of it this way. If x is positive, then by squaring x, you don't lose a negative sign, as there is no negative sign to begin with. Take the square root of it, and you get x back. But this is where you have to be careful. If x is negative, then if you square x, you've lost the negative sign. This is now positive. The root of it will still be positive, but x is negative. So there's something wrong here. X is negative, but the root of x squared is positive. To offset this difference, you have to negate the square root. And so if x is positive, x is the root of x squared. If x is negative, x is the negative the root of x squared. And the argument is the same if you had, instead of the square root, the 4th root, the 6th root, the 8th root, and so on. If you have an even root and x is negative, because x is negative and the even root of the eventh power is positive, you have to negate the root to have an equality with x. For odd powers, this is not a problem. Let's look at the cube root, but this will be the same argument for the fifth root, the seventh root, and so on. If you draw now the graph of x cubed, and you want to look at the graph of the cube root function, so again we draw the line y equals x, and we will reflect the curve about this line, and if you do so, that's the first half, second half, you can see that we have actually a function. It is defined everywhere for any x value, and for any x value there is a unique y value, and this is the cube root function. So the problem we had about the square root function no longer exists for the cube root function. For any given value of x, there is a unique value to the cube root of x. And you can see, if x is positive, the cube root is positive. If x is negative, the cube root is also negative. And so here, there is no need to separate when x is positive and when x is negative. If you cube something positive, it's something positive. If you cube something negative, it's something negative. And take the cube root of that, and as we have seen, the cube root of something positive is positive, the cube root of something negative is negative, and so for any given value of x, the cube root of x cubed is always equal to x, whether x is positive or negative. And the same argument works for, say, the fifth root. The fifth root of x to the 5 is always going to be x, same for the seventh root, and so on. No problem when you have odd roots, 3, 5, 7, and so forth. When you have even roots, square root, fourth root, and so on, always be careful that when x is negative, you have to negate the root to have the equality. Let's look at 2 examples or 3 examples to see why this is sometimes a cause for errors. So here's the example. We are letting x approach positive infinity. Notice now that x is positive, very large and positive. We have a fraction, and it's pretty clear when x goes to infinity, both the numerator and denominator go to infinity. So we have an indeterminate case in the form of infinity over infinity. Well, the dominant term on the bottom is x, and it's kind of the same on the top. If you look inside the square root, the dominant term is 4x squared. Ignore the 4, think of the x squared, and the root of x squared will be roughly x. So it looks like we have something x over x. And so we use an old technique. We multiply top and bottom by 1 over x. One over x over itself is just 1, so this is legitimate. We are not changing the expression. Let's multiply the denominator by 1 over x. So we'll get 3 plus 2 over x. The question is now, what do we do with the numerator? We have the root of 4x squared plus 1. And we have this 1 over x here. Now if we hope to cancel with the square root, we have to replace x by the root of x squared. Because x is positive, x is equal to the root of x squared. And so instead of using 1 over x, we'll use 1 over root of x squared. Now think of what's going to happen. We're going to have on top the root of 4x squared plus 1 over root of x squared. this is our numerator, over 3 plus 2 over x. But remember properties of the square root. The root of a over the root of b is just the square root of a over b. So we'll use this idea here. This is the limit as x goes to infinity. Our numerator, the root of 4x squared plus 1 over x squared over 3 plus 2 over x. And now we can obviously divide through both terms by x squared. So we'll have on the numerator the root of 4x squared over x squared is simply 4 plus 1 over x squared all over 3 plus 2 over x. And now the limit is trivial. As x goes to positive infinity, 1 over x squared shrinks to 0 as x squared also goes to infinity. Same argument, 2 over x shrinks to 0. And we're left on the numerator with the root of 4 over 3. Root of 4 is 2, so it's just 2/3. And that's it. Now, let's consider the exact same limit, but instead of letting x approach positive infinity, we will let x approach negative infinity and see if something changes. Right away from the case, we'll see something is different. When x approached positive infinity, we had a positive over a positive infinity case. And now think of it. 4x squared is positive, so the root of this will be positive, so it will go to positive infinity. But 3 times x, as x goes to negative infinity, 3x will also go to negative infinity, plus 2 is negative infinity. So before we had positive over positive infinity, now we have positive over negative infinity. So we may expect the answer now not to be 2/3, but negative of 2/3. Let's verify this. As we've said before, the dominant term on the bottom is x. So we multiply top and bottom by 1 over x. We know that we'll have to change this x by the root of x squared, but here we have to be careful. As x approaches negative infinity, x is very large and negative. So now if you square x and take the square root back, you get x back, but you've lost because of squaring the negative sign. So x is not the square root of x squared, but now the negative of the square root of x squared. So let's see what that gives us. Let's multiply the denominator by 1 over x. We'll get simply 3 plus 2 over x as before. And now 1 over x, replacing x by a negative root of x squared, will give you 1 over the negative of the root of x squared. Well, we have this times 1 over the negative of the root of x squared. We'll pull the negative up front. And now we have the root of 4x squared plus 1 over the root of x squared. And you see everything is exactly as before, except now there is a negative up front, which will give us negative 2/3. Let's complete this in one line. So root of a over root of b will be root of a over b. And we'll divide already, so we'll do 4x squared over x squared is 4, plus 1 over x squared, over 3 plus 2 over x. As x goes to negative infinity, 1 over x squared and 2 over x shrink to 0. And we're left with negative root of 4 over 3. Root of 4 is 2, so it's negative 2/3. So you see, everything was the same as in the previous example. The only difference here, as we approached positive infinity, x were positive, and so x was the root of x squared. But if we approach negative infinity, then x is negative, and so it no longer is equal to the root of x squared, but now the negative of the root of x squared. So always be very careful when you let x approach negative infinity to not forget the negative sign if you have an even root. Let's do two last examples very shortly, one with a cube root and then one with a fourth root. In both cases, we'll approach negative infinity, as this is the only time when there is a potential subtlety. When we approach positive infinity, there's nothing to worry about. So here's the limit. Two x squared plus 1 cube root of x to the 6 plus 4. Well, as x goes to negative infinity, x squared goes to positive infinity. So we have positive infinity over x to the 6, as 6 is even, will go to positive infinity. Cube root will give us positive infinity. So we have an infinity over infinity case. The main term on top is x squared. So we'll multiply top and bottom by 1 over x squared. This will be obvious, but now here, to be able to cancel, we have to rewrite x squared as the cube root of something. Well, if you think of it, x squared is simply the cube root of x to the 6. 6 times 1 over 3 is 2. And here everything is okay. If you think of it, x squared, even though x is negative, right? X squared is positive. X to the 6 is positive. The cube root of a positive number is also positive. So everything is okay here. So we can make the substitution. Multiply by 1 over x squared, you get 2 plus 1 over x squared over, now I'll make the substitution, cube root of x to the 6 plus 4, replacing x squared by the cube root of x to the 6, so over the cube root of x to the 6. Property of roots, cube root of a over cube root of b is the cube root of a over b. And I'll divide in one go. So I'll do x to the 6 over x to the 6 is 1 plus 4 over x to the 6. Oops. X to the 6. And now as x goes to negative infinity, 1 over x squared goes to 0. 4 over x to the 6 goes to 0. So we're left with quite simply 2 over the cube root of 1. But the cube root of 1 is simply 1. So the answer is 2, and that's it. Let's look at one last short example. So 3x plus 1 over the 4th root of 2x to the 4 plus x plus 1. As x goes to negative infinity, 3x goes to negative infinity as well, over, look inside the 4th root, the dominant term is x to the 4, which goes to positive infinity. 4th root of that will be positive infinity as well. So we have a negative over positive infinity. So if you notice, if the limit does exist, we should get a negative answer, as a negative over a positive is a negative. Well, the dominant term on top is the x, so we'll multiply top and bottom by 1 over x. Here though we'll be a little faster. We know that we would do 1 over x over 1 over x, but we want to simplify the 4th root, so we need x to be the 4th root of something. Now keep in mind x approaches negative infinity, so x is negative. And now if you take x to the 4, because 4 is even, you've killed the negative sign. Taking the 4th root back, you will get x back, but you've lost negative sign in the process. So x is not equal to the 4th root of x to the 4, but the negative of the 4th root of x to the 4. And so instead of writing 1 over x, we'll make the substitution right away. 1 over negative the 4th root, negative the 4th root of x to the 4. We can multiply out now and simplify. 3x plus 1 times 1 over x is 3 plus 1 over x. Here we can combine already. We'll leave the negative up front, so negative. The 4th root of a over the 4th root of b is the 4th root of a over b. And we'll already divide through a over b. So 2x to the 4 over x to the 4 is 2, plus x over x to the 4, 1 over x cubed, plus 1 over x to the 4, and that's it. And now clearly as x goes to negative infinity, 1 over x cubed, 1 over x to the 4 all shrink to 0. And so we're left with 3 on the numerator over negative the 4th root of 2. So we can write this finally as the negative 3 over the 4th root of 2. And this is our final answer. And notice that it is negative as we had initially guessed. And that's it. So when x approaches positive infinity, no problem. When x approaches negative infinity, always be careful if you have an even root that x is not the root of the eventh power, but the negative, and that's the only difference. And that's it. With this, you should be able to handle almost any limits at infinity, at least involving powers of x, integer powers, or fractional powers.